Hi, we're going to look at the next bit of circular motion now. We're actually considering some circular motion, something moving in a circular fashion. Essentially, it boils down to two different categories of things moving in a circle. It could be an object moving in a circular path, much like Salty is here, just going round in a circle. Or it could be an object, so I need BoCo because he's a little bit bigger. It could be an object like that actually rotating. So the whole object is rotating and there's different points along the objects transcribing different circles as they move round. Okay, the maths behind both is exactly the same, and there's lots of different contexts and strange ways this can all be examined anyway. So we will cover both as we go through and consider both sort of different scenarios. Other examples. Okay, so think about the wheel of a bicycle or a car. That's a continuous object moving in a circle, like a CD or a record. The whole object moving. Spinning, rotating. You can consider objects that move in circles, so things like a car and a roundabout being a pretty reasonable example. A Ferris wheel, if you that can, you can look at the carriages on the Ferris wheel prescribing a circle, or the Ferris wheel as a whole moving and rotating. A planetary orbit are almost circular, not quite, but quite often they'll be modelled as circular during A level. Clothes in a tumble dryer, spinning just a mass round on a string like a hammer throw, and quite a popular one is particles in a particle accelerator to consider at A-level physics, because there's lots of contexts where they can get other parts of physics into the same questions with that one. Okay, if we're talking about motion, that implies something obviously moving and changing position. And if it's a circular motion, then actually it's going to be the angular position rather than the linear position that you studied earlier on the year that we're going to consider changing. So I'm just going to add a few little details to the diagram here. So what we're doing, I'm just going to put a rough centre point in there. It's probably not perfect. But if we are looking at an object that was at point A and moves in a circle round to another point that we'll call imaginatively point B, going that way round, okay, then it means that at both those points it is a distance of a radius away from the centre of the circle, and it moves through an angle of theta. Okay, so in a given time of t, our object has moved positions from A to B. It's gone clockwise as I've drawn it. That direction is important with this. There will be times where you'll need to consider whether it's clockwise or anti-clockwise. If it's true circular motion, then the radius doesn't change at any point, so it's only the angular position that's going to change as it goes through that. And we can turn that into a motion equation by considering the rate of change of that angular position. That is known as the angular speed. Okay, so angular speed is the rate of change of angular position, and that's sometimes called angular velocity if we're going to include the direction in there as well. Sometimes in other contexts it's called angular frequency as well. We'll watch out for that one a little bit later on as well. Okay, now the definition for that mathematically is quite simple. Angular speed is given the symbol omega. Yes, it looks like a W. Try not to call it W. It's an omega. So omega equals theta, the change in angle, divided by t, the time for that change. Okay, now theta should be in radians, so angular speed is in radians per second. Be careful of the notation there. It's not rads to the -1, it's rad second -1. So it's radian per second. So the unit, the shorthand for the unit for radians is rad, seconds, s -1. Okay, now you will be looking chiefly at uniform circular motion throughout the course. Uniform circular motion means that omega is constant. So in uniform circular motion, omega is constant. Okay, now that's true for our example of just an object moving in a circle. Okay. But more importantly, for some of this, it's also true for examples of objects rotating. So it doesn't matter where on that object we measure, okay, whether it's the buffers or whether it's quite close to the centre, the angular speed is constant for the whole object. Okay, the top bit isn't rotating at a higher rotational speed than the middle, otherwise the object would distort. So it's constant for the whole object. That's going to be key going forwards. Right. Now what we're going to do next is have a little look at what the relationship is then between the linear speed at a given point. I'm going to emphasize I'm using the word speed here, not velocity at this point. The relationship of the linear speed to the angular speed. Okay, so the angular speed is the angle traced out. The linear speed is how physically how far it goes around the outside. So essentially it's the arc length divided by the unit time for the same section of motion that we're looking at there. Okay, it's probably easier, rather than just looking at a small section like that, to consider the entire circle, just to do the derivations a little bit easier. The derivations aren't examinable, but they're useful for you to see where things come from. So if we consider an entire circuit, then we know that v, the linear speed, is the distance divided by the time, where the distance is actually 2 pi r. Okay, the circumference of the circle divided by time. And in terms of angular velocity, I'll change colour just so that you can see the difference. So angular speed, sorry, I should say at this point. So angular speed we've already defined as theta divided by t, and because it's going to go all the way around the circle, okay, that angle is 2 pi over t. And you see those two equations actually end up looking pretty similar. Okay, the only difference being that omega is 2 pi over t and v is 2 pi r over t. And that gives us a really, really beautifully simple equation to work with, which is very straightforward. That the velocity is exactly the same equation as, sorry, the linear speed, I should say, is absolutely the same equation as the angular speed. It's just got a factor of r in there. So v is equal to omega multiplied by r. It's on the formula sheet. Okay, you don't have to learn it, but it probably is one that will stick over time. Just be really careful that you don't get the two different speeds, linear and angular, mixed up. It's easy to get confused in your head which one you're saying. Okay, linear speed, meters per second, angular speed, radians per second. The radius, therefore, has to be in meters. So if you're dealing with a very large radius, such as a planetary orbit, or a very small one, just make sure you do your conversions. Okay, now there's also relationships with time period and frequency, which are relatively straightforward. Again, using the same equations, I'm just going to write these within the circle, so I've got a bit of space, so it's all in one place. So we've got angular speed is equal to theta divided by t. If for the time period, that's the time it takes to do one full circuit, we know that theta is 2 pi. So that time would be the time period. And as frequency, this is traditional frequency, the number of cycles per second. This would be the number of complete revolutions per second. Then frequency is 1 over t. So we simply can write omega is also 2 pi times by the traditional frequency, the revolutions per second. Now, do be aware, quite often questions will give you the frequency in revolutions per minute. So again, there's conversions to be careful of as we're going forward there.